Learning Outcomes 3.1 and 3.2. Describe what is the response of an LTI system to a complex exponential input. Describe how the response of an LTI system to a complex exponential input relates to the Fourier series. In Learning Outcome 2.4, we talked about the relationship between the inputs and the outputs of a system and the system impulse response, h of n or h of t. We said that the inputs were called x, the outputs were called y, and if we put in a special input, such as the impulse, either in discrete time or continuous time, then the output we get out is special. It is the impulse response. We're going to look at a different input now, but that idea that a special input will have a special output is the key to this section of the course. We're going to look at everything in continuous time, but there's something equivalent that exists in discrete time, and you can read about that in your book as an optional topic. We're looking at how when our input is a complex exponential, e to the j omega 0 t, where omega 0 is some constant. If we put this complex exponential into our system, the response of the system, if it's an LTI system, will be that same complex exponential with a scaling factor. And that scaling factor is a function of that frequency. And we'll talk later about how to determine what that is. And we can do that if we know the relationship between our input and our output. And in a future chapter, we'll talk about how to get h of j omega directly from h of t. So now let's move on to learning outcome 3.2. We just introduced how if we have an input that's a complex exponential, we'll get an output that's a scaled complex exponential. Learning outcome 3.2 is how to take that information and relate it to a Fourier series, which is the topic of this chapter. So let's consider if we have a certain input, x1, and that input is a complex exponential e to the j1t, so omega naught is 1. We know that the output will be that same e to the j1t scaled by an h that's a function of that frequency, 1. If we put another input in, which is e to the j2t, so a different omega naught, we'll get another output that's h of j2, e to the j2t. So the same complex exponential, different scaling constant. By linearity, we know that if we were to add these two inputs, that our output will be what? Think back to learning outcome 1.4. It's going to be the sum of these two outputs. We also know, because it's an LTI system, that if we were to scale this first input by some constant value, that the output will be what? Again, think back to learning outcome 1.4, the exercises we did there. It's an LTI system. It's going to be that same output we had for that first input, but now scaled by that constant 5. Okay, now how do we use this for Fourier series? Let's take a little bit more theoretical. If our input is e to the j omega 0 t, previously I gave you a fixed value for omega 0, now we're going to leave it as a variable. The output will be h of j omega 0 e to the j omega 0 t. If our input is e to the j2 omega 0 t, our output will be y2 equals h of j2 omega 0 e to the j2 omega 0 t. If our input is the sum of these two inputs, our output will be the sum of those two outputs. If our input is a scaled version of this input, our output will be a scaled version of this first output. Same idea as we just went through when we had fixed numbers for omega naught. We had fixed values for the constant a1, but now we're doing it with variables. We're applying linearity and time invariance. Now, what if we take this idea here of adding things and scaling things, instead of just doing addition of two things and scaling of one thing, we expand that to where we're going to add an infinite number of complex exponentials with an infinite number of different frequencies, each scaled by a different value. What would our output then be? Apply linearity, apply time invariance. The additivity part of linearity says we're still going to add the pieces, just like we still added in example Y3. We're going to scale each of them by an h, and that h is a function of whatever that frequency is. And we have that a sub k, which is that scaling value that comes along. We can take this h of j k omega naught multiplied by a sub k, and we can call it b sub k. And what we have here is another Fourier series. Instead of calling it with coefficients a sub k, they're called with coefficients b sub k. Still a set of variables, still a set of constants that are added up, scaling each of the different complex exponentials. It's just a Fourier series. And if we know our b sub k's and we know our omega naught, we can determine our y5. And that's our Fourier series in and a Fourier series out.